Hello, this is SND College of Engineering and Research Center, Yevla. Lecture series for first year engineering physics. I, Dr. Chaudhary Vivek Sitaram from first year engineering department. Today's topic is about quantum computing. Now, what is quantum computer? A quantum computer is a machine that performs calculations based on laws of quantum mechanics, which is the behavior of particles at the subatomic level. What is important? Which is the behavior of particles at the subatomic levels. Now in this, we will see about the history. Now, the representation of data or qubits, that is quantum bits. As we know in computers, whatever may be the process is going on in terms of bits. Bits become bytes, then words, and then its memory capacity actually increasing goes on. So bit is a basic unit. So here, as in quantum computers, it is represented quantum bits, that is qubits. A bit of data is represented by a single atom, that is in one of the two states, denoted by position 1 and position 1. A single bit of this form is known as qubit. As in the digital format, in general purpose computers, there are logic systems, that is positive logic system and negative logic system. In positive logic system, some of the voltage near about 5 volt or 3 volt, that is pre-decided volt. If that voltage is switched, then it is represented by 1, and if the below that voltage, that is 0 or 0.5, so it is denoted by logic 0. So it is a positive logic system, and inverse of that, that is negative logic system. Here the bits are represented by logic 1 and logic 1, logic 1 and logic 0. So a single bit of this form is known as qubit. A physical implementation of qubit could use the two energy levels of an atom, an excited state represented by logic 1 and the ground state represented by logic 0. So now in the left hand side figure, you may see there is a nucleus and electron is revolving in their orbits. Consider, if we are giving external energy to this electron, so we will shift that electron will be shifted in the excited state. So light pulse of frequency lambda for time interval t, then that electron will be shifted to the next level, and that will be the logic 1. Now the state logic 0 and state logic 1. Is it clear? Now representation of data, that is by superposition. Now as we know in quantum, the wave function is denoted by the wave function. The wave is denoted by wave function, that is psi. A single qubit can be forced into superposition of the two states, denoted by the additions of the state vectors. So the logic psi is equal to alpha 1 of logic 0 plus alpha 2 of logic 1. So where alpha 1 and alpha 2 are the complex numbers represented, and summation of there is equal to 1. A qubit in superposition is in both of the states, so logic 1 and 0 at the same time. Now in which state it should be? So representation of data in superposition. Light pulse of frequency lambda, when we are allowed on the time interval t by 2, so there is a logic 0, and when it is excited, that electron is transition from its level to the next level. So here it will be the, so consider a 3-bit qubit register and equally weighted superposition of all possible states. So it will give our equation, that is wave function psi is equal to 1 upon under root of square root of 8 to the logic 0 plus 1 upon square root of, why square root of 8? Because it is having the 3-bit positions, that's why. So now data retrieval. It sounds good, too good to be true, or true it is. In general, an n qubit register can represent the numbers 0 through 2 raised to n minus 1 simultaneously. If we attempt to retrieve the values represented within a superposition, the superposition randomly collapses to represent just one of the original value. So here, according to that, we can get. So relationship among the data entanglement. Entanglement is the ability of quantum system to exhibit correlations between states within a superposition. Now if we consider two qubits, each in the state logic 0 and logic 1, a superposition of logic 0 and 1. So we can entangle the two qubits such that measurement of one qubit is always correlated to the measurement of the other bit, so as we are getting the results. So now if we observe quantum computers, so now if we see the AND gate, the basic one of the gate. So as we know the truth table for AND gate, A and B is equal to C. That is, in ANDing operation, in short, there is a dot product multiplication. So A dot B is equal to C. So 0 dot 0 will be 0, 0 dot 1 will be 0, 1 dot 0 will be 0, and only one result, 1 dot 1 is equal to 1. This type of gate cannot be used. We must use quantum gates, because due to the nature of quantum physics, the destruction of the information in gate will cause heat to be evolved, which can destroy the superposition of qubits. So instead of this, we can use quantum gates. In quantum gates are similar to classical gates, but do not have a degenerate output. That is, their original input state can be derived from their output states uniquely. They must be reversible. This means that the deterministic computation can be performed on quantum computer only if it is reversible. Luckily, it has been shown that the deterministic computation can be made reversible by Charles Bennett in 1973. So quantum gates are generally termed as the Hadamard gates, one of the gate. So that is NOT gate, so also known as square root of NOT gate. So Hadamard gate. So here it is one of the application. Now by using quantum gates, so control NOT gate can also be achieved, and multiplication can also be achieved. So here what is important, that is by quantum controlled NOT gates, quantum gates by control NOT gates can also be achieved. What is in our basic level is, we have to see that by using quantum mechanics we can achieve the quantum computations, and quantum computations, by using that quantum computations, qubit key is achievable, and by using that qubit, basic logic gates are achievable, and from that De Morgan's theorem and other many logic systems can be easily solved. So in CCN, gate has been shown to universal reversible logic gate, as it can be used as a NAND gate. As we know, in our digital system, NAND gate and NOR gates, these two gates are generally termed as the universal gates, because we can achieve any gate logic system by using these two gates. So there is a Shor's algorithm for that. So modular algorithm, quantum parallelism, and quantum Fourier transform. So according to the Shor's algorithm, there is a periodicity. So 7 mod 15 is equal to 1, 7 mod 15 is 7 raised to 1 mod 15 is equal to 7, and so as the values will be there. So if we choose n is equal to 15, so according to that, in that algorithm we are having the n to factor an odd integer of n. So here according to that we can choose that, and we are getting that much bits according to that. What is important in this, so by using these quantum gates we can achieve any gates at this level. Thank you very much.